All right, so we're not given a lot of real specific instructions here. We just want to simplify this expression. So we might use our reciprocal identities, we might use our Pythagorean identities, we might use our odd-even identities. We might use all kinds of stuff here. But we want to simplify this down. My number one suggestion is to put things in sines and cosines. We can always express things as sines and cosines, and quite often things will simplify down and become really nice. And some foreshadowing, this simplifies down to be really nice. So let's see what happens. So I'm going to first, again, rewrite everything in sines and cosines. We know that cosecant is the reciprocal of sine. I know that secant is the reciprocal of cosine, so those are being multiplied together. And we're subtracting cotangent. We know cotangent is cosine over sine. So notice again how important those reciprocal and the quotient identities are, so we can change things to sine and cosine. Now I'm going to simplify this. This is simply just 1 over sine theta cosine theta. I'm subtracting cosine theta over sine theta. If we have two fractions, typically we actually want to perform that subtraction or that addition. So let's get a common denominator. I can do that by multiplying the bottom here by cosine of theta and the top by cosine of theta. Now they have a common denominator, so we can add them together, aka make the denominators the same and perform the subtraction on the top. On the top we have 1 minus cosine times cosine gives us cosine squared theta. And that, whenever you have 1 minus or 1 plus or something like that with a squared function, really does remind me of the Pythagorean identity. So I'm going to write that out so I can visualize it. Sine squared theta plus cosine squared theta is equal to 1. Can I rearrange this so that I can replace this with something? Well, if I just subtract cosine squared theta from both sides, they leave over here, and I'm left with sine squared is equal to 1 minus cosine squared. That is my Pythagorean identity. So I'm going to replace that on the top with sine squared theta notice that was the same thing, so I could replace it, substitute it in there. There's sines on the top and the bottom. One sine on the top cancels out with the one sine on the bottom to give me sine of theta over cosine of theta. And we know sine over cosine, that's tangent. Something just so satisfying about performing some we simplify down, we use those identities, and that seeming nonsense at the beginning became tangent of theta. That's what it's. All right, we're looking to simplify again. It just says simplify. We're going to try to get it down into a much easier to digest thing. So once again, we don't really know what we're going to use. It's already actually in terms of sines and cosines here at the beginning, but we, do we want to use our cofunction? Do we want to use our odd even? Or let's just see what jumps out to us. I mean, the first thing I notice is that we have that kind of expression here, and that kind of expression sure does remind me of those cofunction identities. It's already in the form pi over 2, or 90 degrees, minus my angle, or in this case, our variable is just x. But it's in that form, so we know that is the same thing as cosine. Okay, we're looking good already. Notice there's a cosine in both terms. Well, I can factor that out. Cosine x times sine squared x minus 1. Once again, I see I've got like sine squared x minus 1. It does remind me of the Pythagorean identity. So I'm going to write that out and see if I can rearrange this so that it looks more like that. And I can replace that with something. So there's my Pythagorean identity. I want sine squared x minus 1. So I could subtract 1 from both sides. Now I get sine squared x minus 1, which is what I want. But then I still have this plus cosine squared x. And I now have equals 0 on this other side. I want this all by itself, so now I'm going to get rid of this cosine squared x. Move it over here. So now that's gone. I've got sine squared x minus 1 by itself equals a negative cosine squared x. I was trying to get this by itself because that's what's in my parentheses over there. So now I can replace it with a negative cosine squared x. Cosine times negative cosine squared x is a negative cosine cubed x. Once again, the stuff at the beginning, it looks crazy, but it simplifies down to be really nice. So there we go. Okay, we're continuing to simplify using these identities, and it does give us a little bit of hint right here at the top of the example, but I want us to realize that whenever we have two fractions separated by a plus or a minus, I mean, we're pretty much going to want to make one fraction unless there's really a strong reason not to. That's probably going to be our go-to. We're going to look to get a common denominator, and we're going to look to perform that subtraction, make one fraction, and hopefully it simplifies down to be pretty nice. So let's try it out. Again, look at how crazy this is to begin with. What we get at the end will probably look pretty nice, and we'll be pretty satisfied with that. So we need common denominators. I know I'm going to have to multiply this side by cosine on the top and the bottom. So when I do that, I have sine x cosine squared x over cosine x times 1 minus sine of x. Again, I multiply the cosine on the top and the bottom here because I know I need cosine over here. I'm going to have to multiply the top and the bottom on this side by the 1 minus sine of x. And so on 1 plus sine of x times 1 minus sine of x, well, that's two conjugate binomials. That gives us 1 minus sine squared x. Yeah, that's a difference of squares. It would factor be 1 plus sine x, 1 minus sine x, and so we multiply them together, we get that. Boom. On the bottom, we still have our cosine of x, and we're multiplying it times 1 minus sine of x. That was the whole idea. We want to do that so that we can now subtract. Okay? When we subtract, the bottoms stay the same. Cosine of x times 1 minus sine of x. But the top, we've got sine x cosine squared x, and we're subtracting 1 minus sine squared x. Now you're thinking, why didn't you just go ahead and distribute that minus 1 plus sine squared x? Well, that looks a whole lot like the Pythagorean identity to me, and I don't want to ruin that. Remember, the Pythagorean identity is sine squared plus cosine squared equals 1. And so all I have to do is subtract over the sine squared. We get cosine squared equals 1 minus the sine squared. So I know I can substitute right there my cosine squared of x. Okay, so I'm bringing that down right here. I'm going to do what I just said and input that cosine squared of x. On the bottom, I still have cosine of x times 1 minus sine of x. Okay? So again, I substituted that using my Pythagorean identity. Now on the top, I have cosine squared of x in two places. So I should probably factor that out. Cosine squared x, and I'd be left with sine of x minus 1. On the bottom, I still have my cosine of x and my sine of x minus 1. Okay, looking good. I see some things that can cancel out, especially those sine of x minus 1s. There's a factor on the top and the bottom, so I'm starting to look pretty. Cosine squared of x over cosine of x. Yes, one of the cosines on the top can cancel off the cosine on the bottom. This simplified down to be cosine of x. Started